Sulfate stress corrosion cracking damage mechanisms as a part of environment-assisted cracking. Description of sulfate stress corrosion cracking damage mechanisms based on API 571, surface-initiated cracks caused by environmental cracking of copper alloys in sulfate solutions over many years. Most commonly found in heat exchanger tubes, primarily in cooling water services. Here's a detailed description of sulfate stress corrosion cracking damage, covering its mechanisms, causes, characteristics, and implications. Introduction. Sulfate stress corrosion cracking is a form of environmentally assisted cracking where susceptible materials, under tensile stress, experience crack initiation and propagation due to the combined influence of a corrosive sulfate-containing environment and mechanical stress. It is a critical failure mode in various industrial systems, especially those involving sulfate-rich environments. Mechanisms of sulfate stress corrosion cracking damage, includes, number 1 is environment-mediated crack initiation and propagation, corrosive environment. The presence of sulfate ions or SO4 superscript 2 in aqueous environments creates conditions conducive to SCC. These environments often have elevated sulfate concentrations, acidity, or other aggressive chemical conditions, stress concentration, tensile stresses, either residual, from manufacturing, welding, or fabrication, or operational, pressure, thermal stresses, are necessary to facilitate crack initiation. Crack initiation, microstructural features like inclusions, microvoids, or surface defects act as initiation sites, especially under tensile stress. Crack propagation, sulfate ions penetrate the crack tip region, destabilizing passive films and promoting localized corrosion. The combination of mechanical stress and chemical attack leads to crack growth. Mechanisms of sulfate stress corrosion cracking damage. Number 2 is electrochemical processes. The environment at the crack tip often becomes anodic, where localized dissolution occurs. Sulfate ions can influence the electrochemical potential, destabilize protective oxide films, and facilitate further corrosion. Material susceptibility by sulfate stress corrosion cracking damage. Commonly affected materials, includes, carbon steels and low alloy steels. And then also includes certain stainless steels, nickel alloys, and other susceptible metals, especially if they have microstructural features like inclusions or residual stresses. Microstructure factors that susceptible to sulfate stress corrosion cracking damage includes, grain boundaries, phase boundaries, and inclusions can serve as initiation sites. Microstructural heterogeneities influence the susceptibility and crack path. Characteristics of sulfate stress corrosion cracking damage, includes, number 1 is crack morphology, including the following. The first is transgranular or intergranular cracks. Depending on the material and environment, cracks may propagate across grains or along grain boundaries. The second of crack morphology is step-like or branched cracks, typical of SCC, often with characteristic patterns. And the third of crack morphology is microcracks and macrocracks, initiate as microcracks that can coalesce into larger cracks. Characteristics of sulfate stress corrosion cracking damage. Number 2 is fracture features, dimpled or cup-and-cone fracture surface, indicative of ductile failure combined with brittle cracking. Corrosion products, presence of sulfate salts or other corrosion products within cracks. Characteristics of sulfate stress corrosion cracking damage. Number 3 is environmental signatures. Salt deposits or sulfate residues may be visible on the surface, pH conditions often acidic or neutral, with sulfate ion concentrations high enough to promote cracking. Condition factors favoring sulfate stress corrosion cracking damage, includes, number 1, sulfate ion presence, elevated sulfate concentrations in water or process fluids. Number 2, tensile stress, residual or operational tensile stresses exceeding material threshold. Number 3, temperature, moderate to high temperatures can accelerate SCC processes. Number 4, pH conditions. Neutral to slightly acidic environments are most conducive. Number 5, material microstructure, microstructural features like inclusions, residual stresses, or grain boundaries increase susceptibility. Sulfate stress corrosion cracking implications and damage progression, including, number 1, early stage, microcrack initiation at microstructural flaws under tensile stress. Number 2, progression. Microcracks coalesce and propagate, often along grain boundaries or through grains. Number 3, final failure. Rapid crack growth leads to fracture, often with significant loss of cross-sectional area and structural integrity. Number 4, operational risks, including sudden failure of pipelines, pressure vessels, or other components, and leaks, environmental hazards, and costly downtime. Sulfate stress corrosion cracking detection and control. For detection includes the following methods: visual inspection for surface cracks or corrosion deposits, non-destructive testing, ultrasound, radiography, dye penetrant, monitoring for unusual stress patterns or corrosion rates. Sulfate stress corrosion cracking control measures includes the following methods or strategies: material selection resistant to sulfate SCC, stress relief and minimizing residual stresses, controlling sulfate concentrations in process fluids, pH adjustment to less favorable conditions for SCC, applying protective coatings or cathodic protection. Sulfate stress corrosion cracking is a deterioration process driven by the synergistic effects of sulfate-rich environments, tensile stresses, and susceptible microstructures. It manifests as crack initiation and propagation along microstructural features, often leading to sudden, catastrophic failure if undetected. Understanding the environmental conditions, material susceptibility, and crack morphology is crucial for prevention, early detection, and maintenance strategies. Sulfate stress corrosion cracking affected materials based on API 571. Number A, some copper alloys are highly susceptible, especially Admiralty brass. Number B, the 90x10 and 70x30 copper-nickel alloys are more resistant. Here's a detailed explanation of materials affected by sulfate stress corrosion cracking, including their susceptibility, microstructural factors, and typical industrial applications. Introduction. Sulfate stress corrosion cracking predominantly impacts metals and alloys that are exposed to sulfate-rich environments under tensile stress. The susceptibility depends on material composition, microstructure, residual stresses, and environmental conditions. Primary affected materials by sulfate stress corrosion cracking includes: number 1 is carbon steels and low alloy steels. These are widely used in pipelines, pressure vessels, and structural components. Susceptibility of these material to sulfate stress corrosion cracking includes microstructural features, presence of inclusions, such as manganese sulfides, oxysulfides, nonmetallic inclusions, and residual stresses increase vulnerability. Corrosive environment. Sulfate ions facilitate localized corrosion and crack initiation. The application of carbon steels and low-alloy steels commonly in the following facilities, including oil and gas pipelines, water transmission pipelines, structural supports. Primary affected materials by sulfate stress corrosion cracking. Number 2 is stainless steels. Types of material affected by sulfate stress corrosion cracking includes martensitic and ferritic stainless steels are more prone. Austenitic stainless steels generally exhibit better corrosion resistance but can still be susceptible under certain conditions. Susceptibility factors that material affected by sulfate stress corrosion cracking includes microstructural heterogeneities, presence of microvoids or inclusions, residual stresses from welding or fabrication. The application of stainless steels commonly in the following facilities, including chemical processing equipment, piping systems in sulfate-rich environments. Primary affected materials by sulfate stress corrosion cracking. Number 3 is nickel and nickel-based alloys. For examples, Inconel, Monel, Hastelloy. The susceptibility factors, generally, more resistant but can be affected if microstructurally compromised or under high stress. The applications of nickel and nickel-based alloys, including at the high temperature and corrosive environments, and at the heat exchangers and reactors. Primary affected materials by sulfate stress corrosion cracking. Number 4 is other alloys and materials, includes copper alloys. Certain copper alloys may experience localized attack, especially if microstructural features favor crack initiation. Titanium and its alloys, usually resistant but can be affected if microstructural or environmental conditions favor SCC. Microstructural and mechanical factors influencing susceptibility of sulfate stress corrosion cracking includes inclusions. non-metallic inclusions like manganese sulfides serve as initiation sites for cracks. Residual stresses, stresses from welding, machining, or fabrication can exceed critical thresholds. Microstructure, fine-grained or heterogeneous microstructures may influence crack paths. Surface condition, surface defects, roughness, or corrosion pits increase risk. Environmental conditions that affect material susceptibility includes high sulfate concentration, environments with elevated sulfate levels, such as produced water from oil/gas extraction, wastewater, pH conditions, neutral to slightly acidic environments are most conducive. Temperature, moderate to high temperatures accelerate SCC processes. Presence of chlorides or other ions can exacerbate corrosive effects. Most susceptible materials are those with microstructural heterogeneities, inclusions, or residual stresses. Susceptibility increases in environments with high sulfate concentrations, especially when combined with tensile stress and certain pH or temperature conditions. Material selection, proper fabrication, and stress management are critical to mitigate sulfate SCC. Sulfate stress corrosion cracking damage mechanisms. Critical factors based on API 571. Number A. Susceptible alloys may suffer cracking under the combination of stress and the presence of sulfate chemical compounds. Residual stresses are sufficient to promote cracking. Number B. The process environment must contain sulfates as part of the process or where sulfates can form due to reactions with other chemical species. Number C. Ammonia is usually present, often at very low concentrations. Number D. Cracking usually occurs over a period of many years, sometimes taking as long as 10 to 15 years to cause tube leaks. Here's a comprehensive, detailed explanation of the critical factors influencing sulfate stress corrosion cracking. These factors determine the likelihood, initiation, and propagation of SCC in susceptible materials exposed to sulfate-rich environments. Introduction. Sulfate stress corrosion cracking is a complex interplay of environmental, material, and mechanical factors. The critical factors are those parameters that must reach specific thresholds or conditions to enable crack initiation and propagation. Understanding these factors is essential for predicting, preventing, and controlling SCC. Critical factors influencing sulfate stress corrosion cracking or SCC includes, number 1 is environmental factors, includes, number A, sulfate ion concentration, role. High sulfate ion concentrations increase the likelihood of localized corrosion at crack tips. Sulfate ion concentration details, sulfate ions, SO4 superscript 2, penetrate microcracks and interact with the metal surface. Elevated sulfate levels disrupt passive films, destabilizing the protective oxide layers. Threshold, there is often a critical sulfate concentration above which SCC becomes probable. Below this, the environment is less aggressive. Sulfate ion concentration threshold, there is often a critical sulfate concentration above which SCC becomes probable. Below this, the environment is less aggressive. Environmental factors. Number B is pH of the environment, role, near neutral to slightly acidic conditions favor sulfate SCC, pH of the environment details, acidic environments accelerate metal dissolution at crack tips, neutral pH environments with high sulfate levels can still promote SCC, pH of the environment implication. Maintaining pH outside this window can mitigate SCC risk. Environmental factors. Number C is temperature, role, elevated temperatures accelerate electrochemical reactions and diffusion processes. Temperature details, higher temperatures increase crack growth rates, certain materials become more susceptible at specific temperature ranges. Temperature threshold, there is often a critical temperature above which SCC risk increases significantly. Environmental factors. Number D is presence of other ions, chlorides, halides, and other aggressive ions can synergistically enhance sulfate SCC, implication, environments with multiple aggressive ions are more damaging. Number 2 of critical factors influencing sulfate stress corrosion cracking is coming from material itself, includes, number A, microstructure, inclusions, non-metallic inclusions such as manganese sulfides act as initiation sites, grain boundaries microvoids or precipitates can facilitate crack initiation, residual stresses, tensile residual stresses from welding, fabrication, or deformation increase susceptibility. Material factors. Number B is alloy composition, corrosion resistance. Alloys with stabilizing elements, e.g., chromium, nickel, tend to resist SCC better. Microstructural homogeneity. Uniform microstructures are less prone to localized attack. Material factors. Number C is surface condition, surface roughness and defects. Pits, cracks, or corrosion pits serve as initiation points. Coatings, absence or failure of protective coatings increases exposure. Number 3 of critical factors influencing sulfate stress corrosion cracking is coming from mechanical factors, includes, number A, tensile stress, type of stress. Both residual and operational tensile stresses can initiate and propagate cracks. Threshold stress. There exists a critical stress level, often below the yield strength, above which SCC can occur. Stress concentrations, notches, welds, or surface defects amplify local stresses. Mechanical factors. Number B is stress intensity and duration. Stress intensity. Higher local stresses increase crack initiation probability. Duration. Prolonged exposure under tensile stress facilitates crack growth. Number 4 of critical factors influencing sulfate stress corrosion cracking is coming from microstructural and physiological factors, includes, number A, microvoids and microcracks. Microstructural flaws act as nucleation sites. Their presence and size influence SCC susceptibility. Number B, passive film stability. The stability of oxide films on the metal surface is critical. Sulfate ions destabilize passive films, making the metal surface more vulnerable to localized attack. Number 5 of critical factors influencing sulfate stress corrosion cracking is coming from external factors, includes, number A, mechanical loading conditions. Cyclic loading or stress fluctuations can accelerate crack initiation and growth. Number B, environmental variability. Changes in temperature, flow velocity, or chemical composition over time influence SCC behavior. The critical factors for sulfate SCC are interrelated. The presence of a susceptible material microstructure, tensile stresses, and an aggressive sulfate-rich environment at favorable pH and temperature conditions are necessary to initiate and sustain SCC. Managing or altering these factors, such as reducing residual stresses, controlling environmental chemistry, or selecting more resistant materials, can effectively mitigate the risk of sulfate SCC damage. Sulfate stress corrosion cracking damage affected units or equipment. Based on API 571, sulfate SCC is most often associated with tubes and heat exchanger bundles in overhead distillation systems where sulfates can form or are present in low concentrations. Crude tower overhead exchangers are one example where this form of damage has been observed. Here's a detailed overview of units or equipment commonly affected by sulfate stress corrosion cracking, SCC. I'll explain in depth the types of equipment, their typical environments, and why they are susceptible to SCC damage. Introduction. Sulfate SCC is a localized form of corrosion cracking that occurs under tensile stress in sulfate-rich environments. It primarily affects metallic components in industries such as oil and gas, chemical processing, water treatment, and power generation. The susceptibility depends on the material, environment, and operational conditions. Affected units and equipment by sulfate stress corrosion cracking includes, number 1 is pipelines, includes, number A is oil and gas transmission pipelines. Steel pipelines conveying hydrocarbons, produced water, or other fluids. These pipeline susceptibility factors are including, produced water often contains high sulfate concentrations, welding residual stresses and mechanical stresses from pipeline operation, corrosive environments in offshore or onshore settings. These pipelines' damage pattern includes, localized cracks often initiate at weld zones or surface defects. Cracks propagate along the pipeline wall, risking leaks or failures. These pipelines' damage pattern includes, localized cracks often initiate at weld zones or surface defects. Cracks propagate along the pipeline wall, risking leaks or failures. The affected units and equipment by sulfate stress corrosion cracking. Number 2 is pressure vessels and storage tanks, includes, containers holding chemicals, hydrocarbons, or water under pressure. Its susceptibility factors is including, sulfate-containing fluids in the process, residual stresses from fabrication, welding, or operational pressures, microstructural inhomogeneities. Pressure vessels and storage tanks damage mode includes cracking initiates at welds, nozzles, or corrosion pits. Long-term crack growth can cause leaks or catastrophic rupture. The affected units and equipment by sulfate stress corrosion cracking. Number 3 is heat exchangers and condensers. That is equipment used in chemical processing, power plants, or oil refining. Its susceptibility factors is including corrosive fluids or condensates containing sulfate ions, elevated temperatures accelerating SCC, microstructural heterogeneities and residual stresses. Its impact is crack initiation at welds or surface imperfections, leading to leaks and equipment failure. The affected units and equipment by sulfate stress corrosion cracking. Number 4 is pump and valve components. That is mechanical parts such as casings, stems, and seats. Its susceptibility factors is including sulfate-rich process fluids, operating stresses from cyclic loading, surface defects or corrosion pits. Its impact is premature failure, leakage, or operational disruptions. The affected units and equipment by sulfate stress corrosion cracking. Number 5 is offshore and subsea equipment such as subsea pipelines, risers, and processing units. Its susceptibility factors is including high sulfate concentrations in seawater, elevated pressures and tensile stresses, microstructural vulnerabilities due to fabrication. Its impact is difficult and costly repairs. Potential environmental hazards. The affected units and equipment by sulfate stress corrosion cracking. Number 6 is reactor and process vessel components including internal and external components in chemical or nuclear reactors. Its susceptibility factors is including exposure to sulfate-containing process streams, elevated temperatures and stresses, microstructural features, welds, and residual stresses. Its impact is cracks can compromise structural integrity and safety. The affected units and equipment by sulfate stress corrosion cracking. Number 7 is ancillary structures and supports including structural supports, bracing, and attachments. Its susceptibility factors is including tensile stresses from load or thermal expansion, microstructural inhomogeneities, environmental exposure to sulfate-rich atmospheres or water. Sulfate SCC can affect a wide range of critical equipment and units across industries. The most vulnerable are those operating in sulfate-rich environments under tensile stress, especially if the materials have microstructural heterogeneity or residual stresses. Recognizing these units allows for targeted inspection, maintenance, and mitigation strategies to prevent catastrophic failures. Sulfate stress corrosion cracking appearance or morphology of damage based on API 571. Number A, exchanger tubes show single or highly branched cracks on the surface. Number B, upon metallurgical examination, the cracks will have a branched, transgranular appearance which may be visually difficult to differentiate from ammonia stress corrosion cracking. Number C, tube failures usually result in slow leaks as opposed to tube rupture. Here's a detailed explanation of the appearance and morphology of sulfate stress corrosion cracking, SCC, damage, describing how it manifests visually and microscopically, along with the typical features observed at different scales. Introduction. The morphology of sulfate SCC is characterized by specific features that distinguish it from other forms of corrosion or cracking. These features develop over the course of crack initiation, propagation, and final failure, influenced by the environmental conditions, material microstructure, and stress state. Appearance and morphology of sulfate stress corrosion cracking damage includes, number 1 is macroscopic appearance, includes, number A, surface features. They are such as linear or branched cracks. The most prominent feature of sulfate SCC is the presence of long, slender cracks that often follow a linear or branching pattern. These cracks typically run parallel to the applied stress direction. The next for the surface features is discontinuous or intermittent cracks. Cracks may appear as intermittent segments with rough, jagged edges. They can be smooth or slightly rough depending on the crack growth stage. The next for the surface features is corrosion pits or pitting. Before cracking, corrosion pits or localized corrosion zones may develop, serving as initiation sites. These pits are often rounded, hemispherical, or irregularly shaped and can be deep or shallow. And the last of the surface features is fracture surface appearance. When the crack propagates to failure, the fracture surface may show a combination of brittle and ductile features. with evidence of intergranular or transgranular cracking. These pits are often rounded, hemispherical, or irregularly shaped and can be deep or shallow. The number B of the macroscopic appearance is visual indicators, includes, the first is coloration, oxide deposits or corrosion products, often flaky or powdery, may be present, sulfate-related deposits can be white, gray, or yellowish, and the second of the macroscopic visual indicators is surface roughness. Areas near crack tips tend to be rougher due to localized corrosion and crack propagation. Appearance and morphology of sulfate stress corrosion cracking damage. Number 2 is microstructural and microscopic features, includes, number A is crack morphology, includes, transgranular versus intergranular, cracks can propagate through grains or transgranular, along grain boundaries or intergranular. Sulfate SCC often exhibits intergranular cracking, especially at stress concentrations and microstructural heterogeneities. The next of crack morphology is crack shape, slender, narrow fissures with a straight or slightly curved path. Crack width can be in the range of micrometers or less. Number B of the microstructural and microscopic features is fracture surface features, includes, step-like features. The fracture surface may show step-like features or striations, indicative of cyclic or progressive crack growth. The next of fracture surface features is microvoids and microcracks, presence of microvoids along grain boundaries or within grains. These microvoids coalesce to form cracks. The next of fracture surface features is corrosion products. Sulfate SCC surfaces often have layered or flaky corrosion products. These can be sulfate salts, oxide films, or mixed corrosion deposits. Number B of the microstructural and microscopic features is crack tip features, includes, localized corrosion attack. The crack tip area may show accelerated material dissolution, with rough or etched features. The crack tip often appears blunted or rounded due to corrosion processes, and the next of crack tip is microvoid coalescence, initiation of microvoids at inclusions or microstructural heterogeneities. Appearance and morphology of sulfate stress corrosion cracking damage. Number 3 is metallographic and cross-sectional features, includes, number A is cross-sectional morphology, includes, crack path. The crack may follow a zigzag or rough path, often intersecting grain boundaries. The crack surface can show intergranular propagation. The next of the cross-sectional morphology is corrosion pitting and microcracks. Pre-existing pits and microcracks often serve as nucleation sites, and the next is residual stress zones. Regions around cracks may have residual tensile stresses visible as deformation features. Number B of the metallographic and cross-sectional features is fracture mode, includes, brittle, intergranular fracture, often characterized by flat, shiny fracture surfaces with intergranular features, and then the mixed mode. In some cases, a combination of ductile dimpling and brittle intergranular cracking may be observed. Visual summary, surface view, thin, elongated cracks with possible corrosion deposits, magnified view, intergranular cracks with microvoids, corrosion products, and possibly sulfate salts, cross-sectional view, crack following grain boundaries, often with corrosion pits at the crack tip. The morphology of sulfate SCC damage is characterized primarily by long, slender, often intergranular cracks that develop along microstructural features under tensile stress in sulfate-rich environments. These cracks may be accompanied by corrosion deposits, microvoids, and characteristic fracture features that reveal their propagation mechanisms. Understanding these morphological features is critical for inspection, failure analysis, and developing mitigation strategies. Sulfate stress corrosion cracking damage prevention and mitigation. Based on API 571, number A, it has been suggested that the life of susceptible copper alloy exchanger tubes may be lengthened by periodic cleaning once every 5 years, but limited published information is available to support this claim. Number B, alloys that are highly resistant to ammonia stress corrosion cracking such as the 90-10 Cuny and 70-30 Cuny alloys are also highly resistant to sulfate SCC. Number C, non-copper-based alloys are immune from this form of damage. Here's a comprehensive and detailed explanation of prevention and mitigation strategies for sulfate stress corrosion cracking, SCC. These approaches involve material selection, design considerations, operational controls, and inspection regimes aimed at reducing the risk of SCC initiation and propagation. Prevention and mitigation of sulfate stress corrosion cracking damage, includes, number 1 is material selection, includes, number A, use of SCC-resistant materials, includes, corrosion-resistant alloys, select alloys with high resistance to sulfate SCC, such as certain stainless steels, for example 316L, 2205 duplex stainless steels, nickel-based alloys, or specially treated carbon steels. Microstructural control, use materials with refined grain structures, minimal inclusion content, and controlled residual stresses, coatings and linings, apply protective coatings, for example epoxy, polymer linings, or ceramic coatings, to prevent sulfate ingress and isolate the metal surface from the environment. Number B of material selection is avoiding susceptible materials. Avoid using materials known to be highly susceptible to sulfate SCC, such as certain high-strength steels, or weld metals that are microstructurally vulnerable. Prevention and mitigation of sulfate stress corrosion cracking damage. Number 2 is design considerations, includes, number A is minimize stress concentrations, includes, design for low residual and operational stresses, avoid sharp corners, abrupt changes in cross-section, or weld geometries that induce high residual stress, use stress relief heat treatments after welding or fabrication. And the other ways to minimize stress concentrations is by implement stress relief measures, post-weld heat treatment to reduce residual tensile stresses, stress relief annealing in critical components. Number B of design considerations is avoid environments favorable to SCC, control environment exposure, designed to minimize water retention and sulfate accumulation, use drainage pathways to prevent sulfate-rich water stagnation. Prevention and mitigation of sulfate stress corrosion cracking damage. Number 3 is environmental control, includes, number A is water chemistry management, includes, reduce sulfate concentration, treat process fluids or water sources to lower sulfate levels, use ion exchange, filtration, or chemical inhibitors, and the other ways to prevent from environment factors is by control pH and temperature, maintain pH outside the critical range for SCC, usually neutral to slightly alkaline conditions, avoid high temperatures that accelerate SCC. Number B of environmental control is by dehumidification and moisture control, prevent moisture accumulation on equipment surfaces, especially in humid or offshore environments, use dehumidifiers, protective enclosures, or coatings to reduce water ingress. Prevention and mitigation of sulfate stress corrosion cracking damage. Number 4 is stress management, includes, number A is reduce residual stresses, includes, post-weld stress relief, heat treatments to reduce welding residual stresses, mechanical stress reduction, use of pre-stressing, controlled loading, or relaxation techniques. Stress management. Number B is operational stress control. Limit internal pressures and tensile stresses during operation, avoid cyclic loading or shocks that can promote crack initiation. Prevention and mitigation of sulfate stress corrosion cracking damage. Number 5 is protective coatings and barriers, includes, number A is apply protective barriers, use coatings, linings, or claddings to isolate susceptible metals from sulfate-rich environments. Protective coatings and barriers. Number B is cathodic protection. Employ sacrificial anodes or impressed current systems to reduce the electrochemical potential and slow corrosion processes. Prevention and mitigation of sulfate stress corrosion cracking damage. Number 6 is inspection, monitoring, and maintenance, includes, number A is regular inspection, includes, use non-destructive testing or NDT methods such as ultrasonic testing, radiography, dye penetrant, or eddy current testing to detect early cracks or corrosion pits, focus inspections on weld zones, microstructural weak points, and areas with residual stresses. Inspection, monitoring, and maintenance. Number B is monitoring environmental conditions, includes, install sensors to monitor sulfate concentrations, pH, temperature, and stress levels, use corrosion coupons or probes to assess the corrosion rate. Inspection, monitoring, and maintenance. Number C is preventive maintenance, includes, remove corrosion deposits, clean surfaces, and repair damaged coatings. Replace or refurbish vulnerable components before failure occurs. Prevention and mitigation of sulfate stress corrosion cracking damage. Number 7 is operational strategies, includes, number A is control process conditions, adjust process parameters to reduce sulfate exposure or environmental aggressiveness. Number B is implement stress ramping, gradually increase operational stresses to prevent sudden crack initiation. Number C is limit exposure time. Minimize the duration equipment operates under high stress, sulfate-rich conditions. Preventing and mitigating sulfate SCC requires a comprehensive approach that combines material science, thoughtful design, environmental control, operational practices, and regular inspections. The goal is to eliminate or reduce the factors that promote crack initiation and propagation, thereby enhancing the longevity and safety of equipment exposed to sulfate-rich environments. Sulfate stress corrosion cracking damage inspection and monitoring based on API 571. Number A, inspect heat exchanger tubes for cracking using EC or visual inspection. Number B, physical bending of sample tubes can also be performed to detect shallow cracks indicative of sulfate SCC in the beginning stages. Detecting sulfate stress corrosion cracking is critical for maintaining the integrity of components exposed to sulfate-rich environments. Because SCC often initiates internally or along microstructural features before visible signs appear, a combination of non-destructive testing or NDT and monitoring methods are employed. Here is a detailed overview. Inspection and monitoring methods for detecting sulfate stress corrosion cracking damage. Number 1 is visual inspection. This is the most straightforward and initial inspection method. Suitable for surface exposed areas, the application of visual inspection are including, look for surface cracks, corrosion deposits, discoloration, or pitting, use magnifying lenses or borescopes for hard-to-reach areas. The limitation of visual inspection is not effective for internal cracks, surface cleanliness is essential for accurate detection. Inspection and monitoring methods. Number 2 is liquid penetrant testing. It uses dye penetrants applied to the surface to detect surface breaking cracks. The application of liquid penetrant testing are including, suitable for detecting surface cracks and cracks with open surfaces, effective in detecting via cracks or crack indications that may be precursors to SCC. The limitation of liquid penetrant testing is cannot detect subsurface or embedded cracks, surface must be clean and dry before testing. Inspection and monitoring methods. Number 3 is ultrasonic testing or UT. It uses high-frequency sound waves to detect internal flaws. These techniques include conventional pulse echo and phased array ultrasonic testing. The application of ultrasonic testing are including, detects internal cracks such as those caused by sulfate SCC, can measure crack length, depth, and growth over time, suitable for thick materials and welded joints. The advanced technique of ultrasonic testing are including time-of-flight diffraction or TOFD, high-resolution detection of small cracks. And phased array UT, provides detailed imaging of crack location and orientation, and the limitation of ultrasonic testing is requires skilled operators. Crack detectability depends on orientation and size. Inspection and monitoring methods. Number 4 is radiographic testing or RT. It uses X-rays or gamma rays to produce images of internal features. The application of radiographic testing is to detect internal cracks or flaws associated with SCC. Suitable for thick components or complex geometries. The limitation of radiographic testing is less effective for very small cracks, requires access to both sides of the component. Inspection and monitoring methods. Number 5 is eddy current testing or ECT. It an electromagnetic induction method sensitive to surface and near-surface flaws. The application of eddy current testing is to detect surface breaking and near-surface cracks. Useful for inspecting metallic surfaces with complex geometries. The limitation of eddy current testing is less effective for deep cracks, surface must be conductive and clean. Inspection and monitoring methods. Number 6 is acoustic emission or AE monitoring. It detects transient elastic waves generated by crack growth or corrosion events. The application of acoustic emission monitoring is a real-time detection of active crack growth. It useful in operational environments for early warning. The limitation of acoustic emission monitoring is requires specialized equipment, may produce false positives from other sources. Inspection and monitoring methods. Number 7 is stress and corrosion monitoring, includes, number A is strain gauges and stress monitors. Measure residual or operational stresses that could predispose to SCC. Number B is corrosion coupons and probes. Expose materials to service environments to monitor corrosion rates and sulfate levels. Number C is environmental sensors. Measure sulfate concentration, pH, temperature, and humidity. Inspection and monitoring methods. Number 8 is advanced NDT and inspection techniques, includes. Number A is guided wave ultrasonics. Capable of inspecting long lengths of pipe or tubing for early crack detection. Number B is digital radiography and computed tomography or CT. It provides detailed 3D imaging of internal flaws. Number C is magnetic flux leakage or MFL. It detects corrosion and cracks in ferromagnetic materials. Inspection and monitoring methods. Number 9 is monitoring strategies and best practices, includes. Number A is regular scheduled inspections, establish inspection intervals based on risk assessments. Number B is inspection of critical areas, focus on weld zones, high-stress regions, and environments with high sulfate levels. Number C is use of multiple methods, combined surface inspections, visual, dye penetrant, with internal methods, ultrasound, radiography, for comprehensive assessment. Number D is data recording and trend analysis, track crack growth over time to predict failure and plan maintenance. And number E is continuous monitoring, implement real-time sensors, AE, strain gauges, in high-risk areas for proactive detection. Detecting sulfate SCC involves a multi-method approach tailored to the component geometry, environment, and criticality. Early detection of microcracks or corrosion allows for timely maintenance, preventing catastrophic failure. Combining surface inspections with internal non-destructive methods and environmental monitoring provides the most effective strategy for managing sulfate SCC risks. Thank you.